number 7. All right, so we want to find the surface area of a square right pyramid. Lengths are given in centimeters.
Can you tell that we love surface area?
What's that?
Can you tell that we love surface area?
Yes.
Are you going to put some of the answers in the center so we can make sure we're doing it right?
Yeah. I just don't usually put those up right away, so you guys have a chance to struggle. Shots.
Do we have class on Monday?
We don't, but we can meet if you guys want to. Is that a yes?
Yeah, I like doing it just in case.
Sure. Yeah, so let's just meet at the regular time. All right. So it's something. Set it. So anytime you have surface area and triangles are involved, it's a matter of trying to find bases and heights that'll work to each of the areas of the triangles. So I give this length right here. And if it's a right pyramid, then that means the peak is directly above the center. And so let's see, we know that this side is 2. So we have a square base, that's pretty easy. So really all we have to do is figure out what one of these faces is. And once we have that, we've got all of them. So that face right there, and if I just look straight down at it, it's going to look something like this. That side is 2. This side is the square root of 6. So I want to find the area of that. So 2 is a nice number. I'd like to look at that as the base of my triangle, which means I just need to figure out what's the height. And then I have the area of that. So what can I do to figure out the height of that triangle? Yeah, use the Pythagorean theorem. So by drawing that height, I've essentially cut this triangle kind of in half, right? So for the right triangle, what is that short side?
1.
It's 1. So Pythagorean theorem says to get the height, I have to take h squared plus 1 squared, and that's going to be the long side squared. So that means h squared plus 1 equals, what happens when you square a square root? It cancels, that's wonderful, we get a 6. Subtracting 1. H squared is 5, so h must be the square root of 5. All right, so now we know the height. The height here is the square root of 5. So the area of this triangular face here is 1/2 the base, which is 2, times the height, which is the square root of 5. So the area of one triangular face is what then? Square root of 5. How many of those do I have? Got 4 of them. So for the surface area of this whole figure, we've got 4 faces that have an area of square root of 5, and then we have the bottom, which is a square that's 2 by 2. So that must be an area. That must be an area of 4. So that right there would be the total area for that pyramid.
Is that how you want the answers, or do you want us to use decimals?
Usually I say something like state answers exactly unless I ask you to round. What did I do here?
I did no such thing. So I would take a rounded, since I didn't say it, I would take a rounded answer or an exact answer. What's the units of the surface area? If the lengths are given in centimeters, it would be centimeters squared. So to get a better answer, we should write that in.
So if we added those together, you would take a decimal. Or just leave it.
Yeah, you could plug that into your calculator, right, and you would get a decimal version of it. And that would have been okay here too.
I think we would probably one of them where it was like that and it wouldn't make sense.
You wanted the exact answer with square roots?
It wanted it like, it wanted the square roots, but there was like something where it had a 4 or something added to it and it just couldn't figure out. Doesn't matter if the camera will probably.
Okay. All right. What else should we try?
We're going to go 11.
Sure we can. All right. 11. The diagram below, lines L and M are parallel. Can we give the measures of the lettered angles? All right. Have that. New screen so I can draw on it. So this would have been in section 11.4, I want to say. Let's see. Yeah, this is section 11.4. Where this one came from. Oops, on screen. All right. So we had classified a bunch of different angles. We had vertical angles, alternate interior, alternate exterior angles, and corresponding angles with the big classifications of angles we talked about with respect to parallel lines. So again, focusing on that line L here is parallel to line M here. What do we know? So angle beta right there is 56.31. Do we know the angle right next to M to the left there?
Probably would just be 180.
180 minus that. So somebody help me out with the calculator. What's 180 minus that?
123.69.
123.69. So I'm going to need that in a minute. So I'm going to focus on the E, F, G, and H. And I'm focusing on them right now because I started looking at this angle beta right here, and beta is related to this line that crosses the parallel lines. So can you tell me angle beta is related to which angle up there and why?
E.
E because they are, in the classification, corresponding, because they're in the same position with respect to the parallel lines. Yeah, so these are corresponding, so they must have the same measure. So that must be 56.31 degrees also. Is there anything else that's going to be congruent to B here for beta?
Is F going to be 123?
F is going to be 123 because it corresponds to M.
Yeah.
So this is going to be 123.69.
Wouldn't G also be 56?
Okay, there's two reasons we could give it out. Give me one of them.
I don't know.
Okay. Do you want to relate it to beta or E?
E.
E. So they're called vertical angles in that orientation. So E and G are vertical. Vertical angles are always congruent. So that's 56.31. What, does anybody remember the terminology to relate beta to G? Are they inside or outside of the parallel lines? They are inside the parallel line. Are they on the same side or a different side of that transversal line? They're opposite, yeah. So they're alternate interior angles is what we call them. And alternate interior angles are congruent. All right, H, what must H be?
123.
123.69. Could you give a reason?
Corresponds to F.
It corresponds.
Correspond to
No, we don't have corresponding angle to it, but it's vertical to F.
Yeah, that's.
Yeah, if they cut right through another center point, then they're called vertical angles. All right, so I think you guys can pretty easily figure out A, B, C, and D from here, based on those ideas. So what is angle D then? What's the measure of angle D?
56.4.
71.5.
Yeah, so that is related to this line right here. And alpha and D are in the same orientation, so it's going to be the 71.75. 57, sorry.
Now, to get A, you do the same thing that you did to M.
Subtract from 180, yeah, because that's on the other side of a 180-degree angle. Yeah, so we take that away from
Subtract
180.
71.75.
From 180, yep. What do you get when you do that subtraction?
I can't get my calculator.
108.4.
Thank you, 108 point. Yeah, so now we get all of these. C must be 108.43, and B must be 71.57.
So no matter what, you always subtract from 180.
Yeah, so because we have a straight line cutting through there, and this is a straight line cutting through there, a straight angle is 180 degrees. So the angle next to it is always 180 minus, always. What's the word for two angles that add up to 180 degrees? Starts with an S. Supplementary. Yeah, complementary, they add up to what? 90, yeah. So these two angles right here are supplementary. And what helped me remember the difference between complementary and supplementary? Sup is like super, bigger, and complementary. That gets the 180.
All right, that was beautiful math.
What is 14?
Oh, it was the thing we did, actually I have one. We just kind of classified like the different.
Yeah, we drew a diagram of it one day on the board. The book has a similar diagram in it for a hierarchy of quadrilaterals.
Did you do that?
Yeah.
You're so freaking organized.
What
That's
is it?
amazing.
Do you want to make you a copy of it?
Sure. if you don't
Yeah.
mind.
Give me your email, or I guess can I get one?
Yeah.
Yeah, I'll just email to you on Canvas.
Yeah, you guys have access to each other through Canvas. Yeah. Yeah.
You're going places.
Oh, I know what we need to do,
Which-
especially Emily. Draw a concave quadrilateral. I know you struggle with concaves. This is a good one to look at together.
I mean, I can.
Go for it.
On my paper?
Yeah.
A concave.
Quadrilateral.
So we have 4 sides?
Yeah.
Oh, wait, what? Okay. Not possible?
Yeah.
Got it.
Got it. So one version. So if those are two of the lines, I just have to, somewhere I have to start caving in. So from here I could go in and then back out. So kind of like a Star Trek sign. There's other variations on that. All right. So then what I want to think about is what's the measure? Let's see, I think I asked for exterior angles. Is that what I asked for here? No, measure of the interior angles. Okay. The sum of the measures of the interior angles. And the easiest way to approach that is I can draw this diagonal right there, which splits it into two triangles. inside of a triangle, what's the sum of the measures? 180. And if I take all the interior measures of those triangles, it turns out they give me fully all the measures of the angles of the interior of the quadrilateral, right? Because these two angles together, doesn't that give me that full interior angle right there? So I have 180 degrees here, and I have 180 degrees here. So that should be 360 degrees. If you wish, I will have protractors available in class. You can measure all of them, add them up, and write it down. Or we could even whip out GeoGebra if we need to. That would be the interior angle sum.
It's always going to equal 360
On a quadrilateral, it's always 360. Yeah, it doesn't matter whether it's convex or concave. Is this number 15? Is that right? Yeah.
All right, we have time for one or two more.
How do they want us to describe the platonic solids? Like, just how many sides they?
So we described them in class the other day. You were out that day? Yeah, so this would be a question I would put probably on a take-home test, unless I had you have open notes, because you need to see them. Let's just look them up and see what we can do to describe them. Platonic load, platonic solids. Wikipedia, probably I should just, oh, here they are, that's very nice. Yeah, so we have the tetrahedron, and the key features of any solid are, what are the faces? How many faces does it have? How many edges does it have? How many vertices does it have? And so that's what we did to describe them. What was each face like? How many faces were there? How many edges were there? And how many vertices were there? Another descriptor that often you look at in solids are how many edges meet at each vertex. And if it's a platonic solid, that means it's got to be the same all the time. So if 3 edges meet here, it's always going to be 3 edges that meet together. So just kind of looking at
And
key.
there's only 5.
Yeah, and that's the crazy thing. Regular 2-dimensional figures, there's infinitely many, but in 3 dimensions, there's only 5 regular figures. That's it. It's kind of nuts. It turns out 3D gets a little more restrictive in some sense. All right.
Great, taking it back to standard deviations.
Yeah, my recommendation on that one is just plug these into a spreadsheet, and the spreadsheet will do median, mode, mean. You have to do the range yourself, but it'll do standard deviation for you. In Google Sheets makes histograms really easy. They're a little harder in Excel. Box plot you have to make by hand.
Could we go over number 22? Unless you have.
Okay, so I was just kind of playing around one day with that circle folding activity we had, and what kind of geometry I saw inside of there. So the perimeter of the triangle is 18 centimeters. And then from that, can we figure out the large circle is how many times bigger than the small circle? So when we did this activity, we did a lot of comparing. This shape is what of that. It turns out we can look at an inner circle, So do you remember I used two words to describe the outer circle versus the inner circle way back in the beginning of geometry? Remember the words I used to talk about when one is outside and one is inside the figure like this?
I remember you talking about it, but I can't.
Yeah, so one of them is circumscribed. The other one is then inscribed. Yeah, so inscribed is within, circumscribed is without. And to circumscribe a plane figure, that you have to touch each vertex. To inscribe, you have to touch each edge, only at a single point. So those are just touching each other right at that midpoint, and that's it, if you zoomed in on that. All right, let's give it a try.
But the circle, the small circle is not inscribed in space.
No, because that's correct. Yeah, you can't do that. You can only inscribe and circumscribe a circle to a polygon, not a circle to a circle. All right, so
What do we know? We've got the triangle perimeter is 18.
Can we assume because it's a circle that it is an equilateral?
Yeah, that paper folding we did, it did end up being it. So this is straight from that exercise. Yeah, so this is equilateral. So that means one side of our triangle has to be 6 units long. So this length right here, let's do it in blue maybe, is 6. Yeah, so a lot of these problems are just to get you to play around with drawings and try and figure out what you can do. So this length right here is 6. Okay. Now I added some other features in here. Like notice I made a mark that that's a right angle where that line comes through right there. That and we have a lot of symmetry here because this is an equilateral triangle. So what can you tell me about this line right here in terms of symmetry? It's a line of symmetry, yeah. Okay, so and this is a right angle. So take those two ideas and you have some information that's going to be important here.
Base of the right triangle.
Yeah, the base of the right triangle is 3 because of that symmetry. Yeah, there you go. You put those two facts together into one. Okay. So that's kind of good. I have a right triangle here. So I can figure out that medium length side. You notice anything about the long side and the short side? Short side half the long side. What kind of triangle this must be then? 30, 60, 90. And we also know that because this is an equilateral triangle, this must be 60 degrees here, because this must be 60 degrees here, and that must be 60 degrees up there. So that half angle right there must be 30 degrees. So what's the height going to be here? 3 square root of 3 based on the other observation before. So 3 square root of 3, that height right there. Just from the observation about that 30, 60, 90 triangle we had before, if this length is 1, this length right there is a half. And then the medium side is always square root of 3 times the short side, was the observation we made earlier. Yeah, and we could have just used the Pythagorean theorem to figure that out. That would be another way to come up with that. So there's multiple ways to attack this problem. All right, so let's see, what else do we know about this problem here? Some other things we can play with. We have a central point right there. Any other thoughts? So this is related to another problem I brought up in class before. Remember the problem about the, I forget the word for it. It was a geometry problem I asked you guys to do. Which one? No, not that one. Geometry regular polygon. The apothem. That's right. To get the apothem, we have to find the central point of the regular polygon. And one way to find the central point is to take a couple of lines of symmetry and find where they meet. So this is not only the center of the triangle, it's the center of the circles too, that midpoint right there. So we're about out of time, so I'm going to leave you guys hanging on this one because we're right on the edge of getting it. There's almost enough information here for you guys to figure out how the big circle and small circle are related.
I have just like a observation. I don't know if it's correct.
Okay, what is your observation?
But the small right triangle that's in it.
Yeah.
The inside where we measured
Like this one right here, or this one right here?
that one right there.
This one right here, so let me highlight it.
Hypotenuse.
That one right there.
Would that be 2/3 of the height? It just looks like it. I don't
It
know.
looks like it is, okay. So that's one thing we have to verify. It looks like it's 2/3 of that height. Okay, so that's one, so you have a hypothesis, right? It turns out there's another hypothesis you can make looking in that direction there. And they're related. So I'm gonna leave it hanging there. If you guys don't get it by Monday, I will reveal it, I promise. And then on Monday, I'll post or give it to you in class my solutions to these. If anybody wants to take an orange or some pizza with them, please do. Although I can bring the oranges home, I'm not allowed to bring pizza home. I'll get grounded.
Really good.
I know.
I will be very sick.